our next speaker, Simon Felten from Oxford University, and he's going to talk about the logarithmic smoothness of non-d-semistable normal closing schemes.
Actually, I'm not exactly talking about this because it would have been too long. Thanks for the introduction. Thanks for the invitation. Actually, my title today is simply extending block structures across singularity. We have seen already today in Tim's talk block singularity, and you already learned that you can resolve a block singularity. And in this talk, we will instead extend the log structure across the singularity instead of modifying the underlying space. So we resolve the log singularity not by throwing up the underlying space, but by changing the log structure to singularity. So by start A and trying to draw the structure. So try to be clear about block singularities at all. And here comes my favorite example, which many of you have already seen. Which we have been in my previous talks. So as far as spectrum of PV. And you have bar is x0, x1, x2, x3 is equal to t times x0 to the 4 plus 1 to the 4 plus n2 to the 4 plus x3 to the 4 in p3 times the star. I actually already saw this also earlier today, and it maps to S bar via projection. And now I'm looking at the open neighborhood of 0, such that the fiber over 0 is the only singular fiber of this fiber. It is possible because it's a geometric function. It will never tell you on the base. And that's called phi. Now, how does the singular fiber look like? Looks like this. So this would be the intersection complex. That's for a component. This term here is P2. 4 times P2. And there's a log structure of this thing. Namely, let's say H is the central fiber. This is H, and you can get now source. This might take the divisorial log structure, vertical bar, and it maps to S0 if it's the divisorial log structure. This morphism is everywhere vertical, and saturated as a morphism of log schemes, but it's not log smooth everywhere, but it has 24 log singularities. And they are like here. So these are the same one that you saw in over here. So this is the intersection of the singular locus of the central fiber with this plate. And this is also the singularities of the total space. At these points, the divisorial log structure is not smooth. I have a name. The C is this locus. You find this on x24 point. Okay, so questions related to this. I will follow. Let's start. How does ME block structure, this is also EME, this is also SMS. So how does ME behave in CNC? And to answer this question, let us look at omega 1 ES log, these log structures. So this is a sheaf of logarithmic scalar differential forms with the usual universal property, and this thing is not quasi-coherent in CNC. So this is very bad. When we say a log singularity, we do not only mean the thing is not log smooth, we also mean such behavior that the log differential forms are actually not quasi-coherent. And so this is not a new problem. It's a problem that we knew for a very long time, maybe like 20 years. So what was our solution up to now to do this? We worked with partial log schemes. What is a partial log scheme? It's E, and then it's an open subset, E without C, and then the log structure is only defined on this complement. And here the log structures we find everywhere. So this is a morphism of partial log schemes, and it's generically log smooth in the sense of that it's log smooth here, and that the complement of this thing has relative codimension 2 over the base. So this is a morphism of partial log schemes. And okay, but this is actually not that good an idea. So what are the infinitesimal deformations of central fiber H without C, H without C to S0, MS0. Now you can deform them as a morphism of partial logs, which means you take a flat deformation of the underlying scheme together with a log smooth deformation of this open subset. So there's no condition that guarantees that the way how you form the log structure interacts well with the extension of the flat deformation of the underlying scheme to the whole of E or H. So if you do this, then you get quite wild deformation factor, and it was never the one that we actually investigated. Instead, we imposed a local model condition, which meant that we are looking at morphisms of partial log schemes, also on the level of deformations, but they must be of a very specific form that comes from these equations. So we have to do something when we want to do deformation theory. It's not the formalism of partial log schemes itself that already yields a good deformation theory of this thing. And then can we use phi E T without C M E C to S M S to compute chromophyton invariant of I minus 1 T for T not equal to 0. So we would like to compute the log chromophyton invariance of the central fiber, but now try to define a log stable map of that target. But so say you have a base here, maybe a P1, and you are interested in curves where this P1 is contracted into a single point. What should the log structure do? We haven't defined a log structure at this point, or we have defined a log structure for even this omega 1 is not one for here. So what should we do to study the stacks of stable log graphs to this thing? And then there's yet another question that you can ask. I didn't tell you the characteristic K, and that was on purpose because I'm not only interested in characteristic 0 here. So let's say the characteristic of K is equal to T larger than 0. And so this explicit example is log Yout that I gave. So you might expect that its deformations are unobstructed. If this is the case with characteristic 0, I talked about this last idea. So the question is, if I have this thing in characteristic P, are deformations still unobstructed? And of course, deformation doesn't mean all partial, or all deformations of the morphism of partial log since not only those deformations that are controlled by the local model. Now, in the smooth situation, not the log situation, the discrete, the non-logarithmic situation, this is now pure by Brandner and Felten. That this thing is unobstructed given the Gaussian spectrum given rates and state P1, which is not always true in characteristic P, and given that the crystalline homology is short. And they're using methods of derived algebraic geometry to do it. So if you want to use derived algebraic geometry to answer this question logarithmically, then we also have to think about what is a derived partial log scheme. But I mean, you could try to mimic this. E is a derived scheme and then derived log structure on this thing. But the proof that used in characteristic 0 and also this other proof depends on Hodge theory. And our method that we use in characteristic 0 to construct the log-derived complex makes no sense for derived partial log scheme. If we would try to do this, we would get the wrong answer. We would get something that doesn't work for the proof that we have in characteristic 0. So we have to do something to fill in the log structure here if we want to attack this deformation problem with positive characteristic of the derived geometry. And in this talk, I will present you a possible solution problem. So I will explain to you how to extend the log structure across the singularity such that this problem vanishes, such that we can define at least some kind of log maps. I haven't yet analyzed this in more detail, such that in this example, the deformations are the right one on the nose. And this is probably always the case in the Seibert problem, consideration around the Seibert problem, and I mean, any computations here or any actual deformation theory is still something that needs to be done. So today, the formalism to extend the log structure.
You care also about the least characteristic case, so you replace T by a T.
Yeah, I mean, formalism works over the integers. Yeah, I mean, the deformation is a mixed characteristic here, yes. Also in characteristic, in the non-logarithmic case, you are also first deforming over derived PD rings into mixed characteristic, and then you can only descend from there. I mean, in the end, you also get unobstructedness for equal characteristic deformation with positive characteristic, but it is like a short step. Okay, so today, a new formalism of log geometry. mindestens paragraph 1 to do this. Now we come to paragraph 2. So I'm now giving the definition of this new formalism, and at the end we will see an example. And I can't go through step by step to motivate everything in this formalism because for now it's called for that. So the thing that we are looking at today is called an integral sharp lax lock ring. And here's the definition of an integral pre-lax lock ring. And is this still legible, or should I use a different pen?
Other pen.
Other pen. Where did the old one go? Yeah, that's right. No. So we are saying this is the PL log ring. And it's right, C equal PAL, and P is commutative monoid, and A is an abelian group, and we have a map P to A, a monoid homomorphism, and integral means that this monoid homomorphism is injective. The theory of non-integral pre-lax lock rings is far more complicated because you have to take homotopy phenomena already into account or deriving entry. So we are looking at integral ones today only. And then A and then B, for all A in A, we have an abelian group LA. And then for all A1, A2 in A, we have a C bilinear map. Mu A1, A2 from L A1 times LA2 L A1 plus A2. And we have 1 in L0. And this, this is associative and commutative and unital. So you might say that the direct sums of the LAs form the commutative credit ring. And then we have an additional datum for every P in P and A in A. We have a map sigma PA from LP plus A to LA. And I call this thing the strap map. I call this thing the cord. And the image that I have, I call it something like a cable or a rope. And I imagine my I make my ring here geometrically, and then I think of the chords as chords that are tied together by a sigma. And these things must satisfy the obvious conditions that sigma 0A of C is equal to C, and sigma Q, sigma P A times sigma Q P plus A of C is sigma Q plus P A C, and you have a multiplicativity condition is sigma P1 plus P2 A1 plus A2 C1 C2. So you might as well say that you construct a certain category out of this monoid homomorphism, and then the sorting is a lexicmetric monoidal functor into the category. But let's stick with the explicit definition of the thing. So if you have this, then R defined as L0 is a commutative ring, and this is called the underlying ring. Or C equals PAL. So this is an integral free ring.
So can you say what you said again? So you have a lax symmetric monoidal functor from what, A?
Category that I didn't define. So the object that I write A, and the objects, I mean the set of objects of EPA is equal to A, and I mean what is the set of homomorphisms? Let's say the homomorphisms in EPA from an object B to an object A is the set of all P in P such that A plus P is equal to B. And this is a commutative monoidal category. But a symmetric monoidal category in the strictest possible sense.
Your definition is equal to a lax symmetric monoidal functor.
From this, yes. And you can also fix R in the beginning and go into R method. And then you can also
Give an example.
take a derived. Target.
Let's do an example.
Try to derive PJ.
Give an example.
Yeah, I first end my definition and then I give the universal example via a functor from locus to.
You apply to that initially like that?
Yeah, this will. I mean, my plan was to first discuss the performance properties.
Yeah, do whatever you want.
I mean, we will see a very extended example at the end. I just thought it's easier if we. I mean, maybe it's not. Maybe it's easier. Yeah, I'm going to explain my. Going to do an explicit example. Well, let me first finish the definition. So, what is an integral sharp Lax-Lock range? So, there are two conditions. This is an S-L-lock. One condition is the Lax-Lock condition, and it means that sigma P0 from LP to L0 is isomorphism if and only if P in Schross, such that P is invertible. So P times P star is the set of invertible elements in P. So in the functor perspective, this means that the functor is conservative. And the sharpness condition is that P is sharp. And if the thing is not integral, you shouldn't look at sharp things because sharp elements are destructive. But in the integral case, you can sharpen then you can throw away all the homogeneous. So all the natural transformation, all the natural equivalences between the functors become can be forced to be identical by carbon, but only in the case.
Can you remind me what sharp means?
The Px is the set of P in P such that exists Q in P such that P plus Q is equal to 0. And P is sharp if this thing is equal to 0. So if 0 is the only invertible element.
So the first one just becomes the condition that
0, 0 is the only element under the sharpness assumption. But you should think, you should think of making a three-Laxlot ring a Laxlot ring as the moral analog of logification, and sharpening. I shouldn't say choosing a model, but this is strict to one category, in any case, integral or not. And in the integral case, this thing is equivalent to the subcategory where this thing is sharp. But in the non-integral case, you can still sharpen, but then you lose information. Okay, so here's the construct. So we started beta M to R, a pre-lock ring, the integral pre-lock ring. This is the category of integral pre-lock rings. Integral in this case is integral monoid. And when we have this, then we set P to M, A to M group. So now you see how integrality of pre-lock rings corresponds to integrality of lock rings, pre-lock rings, because this thing will be injective if anything. And LA is equal to R times EA. EA is a formal index variable now. And the multiplication is given by C1 EA1 times C2 EA2 is equal to C1 C2 EA1 plus A2. Now this is the multiplication in the ring R. And sigma PA of C times E P plus A is equal to beta P times C times EA. So the strip map, so the map from the monoid into the ring of a lock ring becomes via this formula the strap. And now let me now give you the promised explicit example. One explicit example. So let's take for the lock ring N2 to KXY. And 1, 0 maps to X and 0, 1 maps to Y. So then you have a C2 array of copies of this ring. It's KXY and KXY and KXY and KXY and so on. And then you have multiplication with X, multiplication with Y, and multiplication with X, and multiplication with Y. And 0, 0, and here we have E, yeah, 1, 0, and here's E, 0, 1.
What's that supposed to
Mean
mean?
0, 0, whatever.
Yes.
Wait, sorry, you start with. What's this supposed to be a picture of?
What?
This picture you drawn.
This is a picture of, I mean, here I defined a functor, I think it was length is the notation of this thing, yes, from C ring P log into C ring PLL log int. And this is an example where this is the log ring, so this is M, and this is R, and then P is equal to N2, and A is equal to C2, and for every A here we have a copy of the ring with these formal index symbols, and these are the strut names.
This diagram I'm supposed to think is really extending.
It's C2 index, yeah.
So that's the bunch of LAs, LFAs?
Yes.
Okay.
So this is L00, 0, and this is L10.
And each of the A is just a formal symbol.
Like in one here. I'm still using so. I mean, later R will be equal to KP, and then I need separate formal index symbols for indexing in P and indexing in A. All the by P is still a subset of A. It's a bit like in the research. No. You get several copies of the same element. So now I have a certain time. How much time do I have?
10 minutes.
What?
On
15.
fire.
On fire. Here. I might not be able to get to everything. So we have steering P log int here. And then we have steering int PL log here. And now this functor has a left adjoint. Data, which gives back the logs, the log frame, the pre-log frame. And now the situation is, I mean, here I have log frames. And when I put C ring SLLOG in here, then this diagram becomes Cartesian. And this is the motivation for this list of conditions. So a pre-log log frame is a sharp-log log frame if and only if it's associated with pre-log frame is a log frame. And if you only take this thing, this condition, then it's something which I would call a conservative pre-log ring, which means that beta minus 1 M star is equal to M star. Sorry, beta minus 1 O star is equal to M star without this being an isomorphism. So being an isomorphism corresponds to the sharpness condition and lax logification plus sharpening corresponds to logification. And you also get a kind of explanation of why things go wrong when you try logification without integrality being given, because you're forcing sharpness by logification. Okay, so we have this diagram, and then we also have a C-ring SLOG in here, and this functor is, is it left or right? This thing is left adjoint to the inclusion here. So you can logify in the next picture.
I'm a little lost with the notation. What is the P-log? What's the difference between log and P-log?
And this is pre-log rings.
Pre-log.
Classical pre-log rings.
Okay.
I mean, now classical is the log structure.
Oh,
Ordinary pre-log rings.
when you say logification, you mean the associated log structure.
Yeah, I mean, we have the classical logify, or the ordinary, the Kato logification. And then we also have the Lax logification. And you have a composition here. And this descends up to natural isomorphism. And this is a functor that you know by triangle, and it turns a log ring into a half-Lax log ring. It turns integral log ring into a half-Lax log ring. If you cross integrality, you still have all the adjunctions, but you don't have good property. Okay, so now how do we make this into a scheme? So integral sharp Lax log schemes, and let me put this very brief. It's a topological space with a sheaf of integral sharp Lax log rings, such that if you take ℰxt², then think of a scheme. And now when you start with the integral log scheme nx, then you get x mx triangle. And this thing is an integral sharp Lax log scheme, and this defines a functor from integral log schemes here, which is fully faithful. And again, this functor is totally not well behaved. It's a drop integrality. And this also explains why we need to have this A. I mean, you could say maybe I want to index only by P, because when I have a log structure, these negative things, they are not there. They are only there when I take the groupification of the log structure over its over the ghost sheaf. But you need to do this in order for this functor to be fully fake. Otherwise, there will be more morphisms here. The log structure can't see it, but by inverting everything in P and still requiring the existence of the chord to get to a fake moment in the integral case. Okay, so now comes the important example. Go back to geometry and log singularities. We have a monoid P over x bar, y bar, c bar, u bar, and they are given by this is 1, 0, 0, this x bar, y bar is minus 1, 1, 1. and no, we don't have C, we don't have W. T bar is equal to 0, 1, 0, and U bar is equal to 0, 0, 1. So this is a submonoid in C to the 3, and it's characterized by this thing. And if you take KP, this will be also more to K dx by U divided by x minus U, and it's exactly the thing that we saw in Jim's talk. The example of this looks like this, and that was from log singularity. When they have 0, for example, there is a spectrum of KP. So what can we now do with Lax log structures to improve this thing? Let me directly construct the pre-Lax log ring to spectrum. This thing is so P. Let's call it P prime. P prime will be the pre-Lax log ring. Is P localized in K, where K is equal to n times U bar. A will be C to the 3. So this is what you get when you invert U. And then we have to define the chords, and these chords are as follows. So L A will be K of A plus PK cap PG, where G is now n times T bar. So what are you doing? You start with your P, and I mean this picture is not exactly correct, but kind of fewer picture, but it's still isomorphic. So if U bar is here and T bar is here, then you get PG by moving it down, and you get PK by moving it in the diagonal direction by U, and then you have two non-sharp monoids, and you move one of them by A, and then you intersect. And this is going to define your chord. And now the strap maps are simply given by inclusion, and the multiplication is given by multiplication in the ambient Ka. I mean, they're all in Ka, and Ka is a ring. And the group ring of this again group A, and it's given by multiplication this thing. So in this thing, and it's integral because PK is A. This is the integral pre-Lax log ring, so it can form a spectrum.
So can you slow down and do this a little bit? Can you just repeat this example one more time?
Especially the second part.
You're trying to build an integral.
And how much time do I actually have? I cannot talk very long about this example.
5 minutes.
You're trying to build an integral Lax log scheme.
I'm constructing an integral pre-Lax log ring.
Yeah.
Integral pre-Lax log ring. Right?
And then I take a spectrum.
And the point is that this was a log structure that had a singularity in it.
No, the log structure with the singularity is a different one.
Okay, so this was just an example of how you can start with a smooth log.
No, I just omitted too much stuff.
It's
Because
like
of time
constraints. At the beginning, had this gate iteration.
Yeah.
So this is like a local label at one of the similar points.
Yeah, so there's a singularity in the log
Yeah,
structure, right?
yeah.
Okay, and so you're telling me how to build a pre-Lax, or how to build a Lax log ring that models that log singularity.
So we have this thing here.
Yeah.
And this yields a log structure M. And you can get a second divisorial log structure by taking the whole torus bound thing. And this is which I call HM, which I call the coherent hull. So this is a relative chart. So this is the heap of cases in this thing, and this thing is coherent and log smooth. And now this looks like this. So I'm not drawing the ghost tube of this thing restricted to the central fiber. It's n here, it's n here, it's n2 here, but in the log singularity, the rank drops to n. And this implies that this sheaf of monoids does not admit a shard. And this sheaf of monoids does not admit, because the rank cannot drop in this case. And if it does not admit a shard, this thing cannot be a coherent or a quasi-coherent log structure. So how do we make this log structure coherent? We make it coherent by saying, oh, we don't want n, we want n2 here. How do I get n2? I get it by defining Pm as J lower star of M bar without C. So C is now this point. So I take only this thing, there is the open merge of the complement point. I take this direct image, and this happens to have this dog here, and this happens to be a coherent chain of monoids. Now, how do I see that this thing is coherent? Actually, there is a quotient map here. So I have this thing, and this composition is an isomorphism outside of the log singularity. So this actually is a different extension of this thing across this point. And here we have P. Here we have such a chart, and now we can localize in K here. And this composition factors here, and PK is actually a shard for this thing. So now we have this, and then we said AM defined as J lower star of M bar group. This was mistake. But then we still need to define L. And how do we do this? We do it as follows. We have pi m without c group to m bar group m without c. This is the quotient of the ghost. So if you have an element A in PM or in AM, then we can look at var pi minus 1 of A restricted to let's say it's a cross section M without C. And this is what I call LM without C star A restricted to M without C. And this is an OM star torsor. Now, as an OM star torsor, I cannot generally extend it. This is what happens with this. I mean, this is an O star torsor on the complement of the point. And this thing is, there's still a map and it's injected. And the things here that are not seen by this map are precisely those O star torsors that do not extend as an O star torsor across the point. It is only a copy of N, which is those which extend as an O star torsor. So the source of the non-coherence is throwing away things that don't extend as O star torsors. So what do? We extend it to a line bundle. Every O star torsor defines a line bundle, which I denote now by L M without C, A restricted to M without C.
That's why you call it L. Could have told us that. The line bundle.
It's a line bundle when it comes to logs. And now I can take J lower star, and because C is so small, this is still coherent. This is Lm of A by definition in this example, not for all log singularities, but on this locomorpho. This is now a Sharp-like log structure, and it's precisely the spectrum of this thing. Now I can restrict the thing, and I get a Sharp-like log structure on the central fiber. This no longer has this description with J lower star from proximate locus, which shows that it's not sufficient to always take this direct image. just happens to work in the local model. It no longer works in the central fiber like this. So the sharp-like log structure is more data that we need to have.
But you always get it when you have local models. Because of that.
Yeah, I mean, in historic local models.
Yeah, that's good. Good enough.
Now, why do we believe that this thing that we have constructed like this and this? I mean, you can't take an arbitrary sharp-torque model like this. You need additional conditions for this to work, because you are intersecting PK and PG, and you need to be well behaved, and always work in the field of But why do we believe that this is something that we should look at? And it's because it solves the deformation problem. The problem of defining the correct deformations. Let's look at formal smoothness. So we have this thing. Let's say PM AMLM from the example. And it goes here to S, which is now A1, and PS AS LS. And now you can ask if this satisfies the infinitesimal lifting property. So you say we have T and T prime. Oh. We have T and T prime to other sharp-like log, integral sharp-like log schemes, and then you can a strict infinitesimal thickening. And this thing always exists locally. So this thing is the infinitesimal lifting property in schemes sharp-like slog int. Now I didn't tell you what exactly these thickenings are, but it's not always. Why is it not always so that this thing does have the infinitesimal lifting property? Because this construction does nothing on the nearby fiber. But the nearby fiber is not always smooth. So the smoothness of the nearby fiber in the local model is the precondition for this thing to be to have the infinitesimal lifting property, and it's actually enough. So if the nearby fiber is smooth, then this thing will be also smooth. So the only source of non-smoothness is the non-smoothness that we are seeing in the nearby fiber. Maybe that goes away when we consider these things as false moduli with appropriate stacks. But at least in dimension 3, it means it's always smooth, because, I mean, for Stewart setting. Yeah, I think I end here. I also prepared something more to say about the Stewart situation. The upshot is you can, at least in characteristic 0, always extend the log structure in a coherent way across the log singularities. In a codimension 3, at least it always smooth. And if it's smooth, this explains the local unique logarithmic deformations. Okay, thanks for your attention.